All right, welcome. So today we're going to talk about Ratpack. In yesterday's session, we did a bit of an intro talk, a very high-level view of Ratpack and how you might go about implementing, a REST API. And there was a lot of information embedded in there that I wish I could explain more in depth. And one of the most crucial aspects about working with Ratpack is that Ratpack is asynchronous, non-blocking, reactive, blah, 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 blah. Things that you hear everybody saying these days, but what does that really mean, and what does that really mean for you as users of Ratpack? So this talk is going to be an introduction on how asynchronous and non-blocking works in Ratpack, and some of the surprises that new users experience, and I hope that by the end of this presentation we can get an understanding of how Ratpack works with asynchronous code and blocking code and everything like that, and hopefully this will be kind of eye-opening and draw you into Ratpack. So let's get started. Let's get started by talking about the need for asynchronous behavior in our applications. So essentially, we want to do more with less. What that means is that resources are expensive. No matter where you are, whether you're on premises, whether you're in the cloud, whether you're at some kind of hosted solution, you essentially end up paying for CPU, memory usage, network I/O, right? Anything that generates or increases entropy in the universe is what you're paying for, essentially. So in order of most expensive to decreasing in terms of running or handling web requests, we have certain methods of running your applications, such as forking multiple processes, and you can think of the Apache web server in that regards. And people said, no, that's way too expensive. We shouldn't be doing this. It's just way too much, and you run out of memory pretty quickly. So people said, okay, then let's bring it down to threads. And an example of that would be your servlet container, right, like Tomcat, or perhaps writing your own thread pool-based web handling logic. And then people said, nope, even that's too expensive, and you still have to create threads to handle every single request in a kind of request per thread kind of model. And then people said, you know what, we can do better. And Netty posited that. Netty built off the work of Apache Mina, which worked from before that, and so on and so forth. But really, Netty brings it down with the event loop, and having multiple threads, kind of trying to handle that stuff. So it's not like Node.js where you just have a single thread, single process, and handle requests like that. Netty has several threads that will handle the request for you. And of course, we want to really maximize your bang for your buck, right? So for every dollar you spend, you'd like to be able to handle more traffic, essentially. And there's a really great resource out there. This is the website. It's the C10K. What does that stand for? That's concurrent 10,000 connections, right? And this is all about kind of talking about, well, how can we get to handling 10,000 simultaneous connections on a single node? And since this article has been produced, we've been able to blow that boundary out. And so if you have time, you go through this resource. It's a very good resource. It talks about all the different types of approaches to handling web requests and how I/O works and all the different mechanisms and all the different operating systems. It's a very, very good resource. And if you're a newbie to network programming like I was a couple of years back, this is a really good resource to figuring out, where we've been, where we were, and where we're going. So that's a really nice resource there. So, okay, fine. So you'd like to use asynchronous coding because somehow it allows us to use less resources. Well, what does that look like in terms of the JVM ecosystem? We have primitives for working with asynchronous code. We have threads, executors. We have mutexes in some kind of way, right? Like we have read-write locks. We've got synchronized. We've got the ability to have synchronized lock objects and things like that. And we also have things like atomic references that guarantee atomicity on each operation. But that comes at a price. It means that testing these things are not the easiest thing in the world. Making asynchronous code that's readable, where you can read it and not have it execute to understand what it means, that's also a bit of a challenge as well. And firing off threads and doing asynchronous work is the easy part. It's the coordination of the threads and sharing computed results and essentially sharing memory across threads. That's the difficult part. So async is hard, right? We've got non-deterministic behavior. You fire off a thread. You don't know when it's going to come back. What happens when an error happens? And if you have a kind of complex call graph where you're spawning multiple asynchronous operations, well, then you end up with callback hell. Also error handling and error propagation and things like these. These are very difficult things to do in asynchronous code. Not to mention, I really want to emphasize that the readability of writing asynchronous code is not the most straightforward thing in the world. And oftentimes you end up causing some severe brain damage to yourself. So yeah, this is difficult stuff. So people have over the years tried to address this in different kind of ways. And so we have libraries that come to the rescue. Concurrency is difficult, and different concurrency models have found their way to the JVM in one form or the other. So we've got things like futures, right? And now with Java 8, we've got completable futures, kind of there, kind of not. We've got the idea of working with blocking queues as an example, or using new fork join that came out, I think, in Java 7. Then you have people taking things like actors from like Erlang. So as an example, we've got Akka and we've got gparse that allows you to do these kind of things. Disruptor pattern. How many of you have heard the disruptor pattern? Yeah, this is a really cool paper by the people at LMAX. It's a really cool piece of machinery, and the white paper on it is like really interesting. So if you're interested in looking up on how to do, or if you're interested in what the disruptor is and what it does for you, I recommend looking it up. And we also have the folks at Parallel Universe producing libraries that allow you to produce lightweight threads, or they call them fibers, maybe green threads or something like that. But essentially they allow you to have continuations on the JVM without having to really change the way you write your code so much. And what we're heading towards is a world where we're trying to achieve lock-free concurrency. And the reason we want to do this is because, again, concurrency is difficult. And when you want to coordinate and share memory across threads or across different asynchronous operations, we want to try to reduce any kind of contention that we have on a shared resource. So yet another thing to look up, take a look into lock-free algorithms, data structures. These are all cool things to look into. And of course, just to go into really how difficult kind of memory works, especially in asynchronous world, I definitely recommend reading Alexei Shipalev's blogs about Java memory model and the follow-up, the close encounters of the JMM kind. This is a very in-depth look into how the Java language specification tells you how the memory model should work. And when you throw threads into the mix, it can be quite mind-blowing. So, okay, so how does Ratpack help, right? Well, Ratpack is async, non-blocking, blah blah blah. It's built on top of Netty, but Ratpack's real value add here is that it has its own concurrency model. Really, it's the execution model, and the execution model from Ratpack is really what separates Ratpack from any other asynchronous web framework that's out there. It's not difficult to make an asynchronous web framework or a non-blocking one. But what is difficult is how do you write your framework in such a way that your users don't end up banging their heads against their desk and regretting their career choice at the end of the day. Or maybe they end up hating their manager for forcing them to use something like that. So let's talk about Ratpack's threading model, right? So how many of you are familiar with how Netty works? Yeah, okay, so a brief overview of how Netty works. You have essentially an event loop that registers all kinds of NIO events. So these are things like opening a socket, reading from a socket, flushing to a socket, writing to a socket, right? And all of these are non-blocking operations, which means you schedule this thing to go off, and the main thread that scheduled these IO events just keeps on going and processes any other registered NIO events that come back that you're interested in. What about so the actual IO component doesn't block the main thread, and it's actually executed using a non-blocking mechanism. So on Linux, that would be something like epoll, which Netty has direct support for. Something like on a BSD system, that would be maybe KQ, but if you don't have any of these mechanisms available, Netty will always fall back and create kind of like a select, which is a very old school way of doing kind of NIO stuff. So on this main thread, which Ratpack uses to handle incoming NIO events, you should never block this thread. This is also known as the compute thread in Ratpack. So, well, what about blocking code then? What about things like file I/O, like the old school file I/O? What about things like using JDBC as an example, which is a blocking library? Well, we have an extra thread pool that handles any kind of blocking code that you need to do. So Ratpack's threading model is that we have an event loop that processes requests and NIO events. And then we have a dedicated thread pool for handling any kind of blocking I/O or any kind of long-running code that you would need to run. So that's how Ratpack's threading model is set up. And so let's talk about Ratpack now. So in the context of this threading model in Netty and concurrency issues, Ratpack has an abstraction that is known as the execution. So an execution, it's kind of difficult to explain it, but an execution is essentially made up of execution segments, right? What the hell does that mean? An execution segment is just a bit of code that is scheduled to run at some point. By default, when you create these execution segments, they get queued up in an order such that they get executed in kind of like a serialized first in, first out kind of manner. So that sounds a little bit abstract, okay? What happens is as a client connects and a connection to your server and a connection is established, Ratpack does a couple of things to set up your execution, your registry, whatever, and then it actually initiates your request processing by creating an execution, queuing up the first execution segment, which is to handle your chain, and then it goes in there. And then from the chain, you then produce additional execution segments. I understand that this will take a couple of times to get through, but what we'll talk about in specific are the promise, operation, and blocking facilities that Ratpack provides. And these are facilities that allow you to hook into the execution and create execution segments and be interested whenever interesting things come back from the execution segment. So just to sum it up, essentially an execution is a collection of execution segments, and Ratpack manages this, and you can use the promise, operation, and blocking facilities to schedule and work with whenever Ratpack returns you values from the execution segment. Some things to know about executions in general. Execution segments they're always executed on the same thread, which means that we have thread affinity for a given execution. So what this means in practice is that by default, you do have thread safety to a degree. So if you have some kind of shared resources that is being accessed across your multiple execution segments, you don't have to synchronize access to it, which is really nice. You don't have to use any concurrency collections or anything like that. So Luke Daly, who is the creator and the visionary behind Ratpack, has a couple of blog posts that go into explaining how the execution model works in more depth. And these two links are blog posts that he talks about the execution model. So there's that one, and then there's this one. These notes aren't published yet, but I will publish them after the presentation. They will be available. I'll put them on Twitter, which is a great time to plug. If you're not following me on Twitter, that's my Twitter handle. So that's how you get access to these notes. All right, so let's talk about Ratpack's async facilities or primitives that are provided, right? So we talked about a promise, we talked about an operation, and we talked about blocking. Typically, when you're working in an asynchronous framework, you need to have something that represents a value that will be computed and made available in the future. And as discussed before, we have things like futures on the JVM, we have callables, we have something like that. We have promises in JavaScript now, right? But the main thing that I'm going to show you today is that Ratpack promises do not behave like promises in any other asynchronous framework. And we'll show you how that works. And another thing that you may not appreciate now, but you may appreciate as you use Ratpack more, is that if you can't find a method in any of these classes, you can actually always build it yourself. So Ratpack you can build the behavior yourself, making use of execution and exec controller APIs. I won't get into that today. That's pretty low level, and I think talking about promise operation and blocking will help you think more in terms of how Ratpack works with asynchronous code. So, promises and operations. Just to go over some high-level points, creating promises schedules execution segments, right? So every time you create a promise, we're actually queuing up an execution segment to be executed later on. Promises are executed in the order they were created. There is an exception for forked promises, but whenever you fork a promise, you're actually forking a brand new execution. But we'll get to that later. They typically, whenever the promises get resolved, they run on the CPU thread. But if you're using the blocking facility, then it runs on the blocking thread pool. So if you by the time you create a promise, it's you pretty much know if the code is going to be running on CPU thread or on the blocking thread. Another thing about Ratpack is it would be completely useless if you couldn't tie it back to use and leverage existing libraries, right? And so Ratpack provides facilities within the promises and operations that allow you to easily adapt your code to blocking code, to asynchronous code, to code that has its own kind of threading model. So an example that I like to use is RxMongo as an example. Or if you're using like an old library that uses thread pools, maybe for executing their asynchronous code. So let's talk about testability. Ratpack provides a first-class test fixture for working with asynchronous code, and that test fixture is called the exec harness. The exec harness will spin up your compute and your blocking thread pools without bringing up an entire Ratpack server, which is low overhead anyways. But the exec harness will allow you to run and experiment and make assertions against promises. So I think there was a question yesterday about, is it possible to test, unit test promise and asynchronous behavior? And the question is yes. And all of our examples that we will go through today will be making use of the exec harness. Some couple of notes about the exec harness. So it is of type auto-closable, which means that you can use the nice Java 7 syntax where you do try with resources and then it'll take care of cleaning itself up. Or if you're using a testing framework such as Spock, you can make use of the cleanup or closable annotation. We also have a lot of convenience methods in the exec harness that allow you to manage the lifecycle of the thread pools that you don't have to clean up yourself. So let's take a look at the main two methods that we'll be using today with the exec harness. So number one is yield. This is great for unit testing. Essentially, you yield a promise using exec harness.yield, and exec harness will take care of executing your promise and figuring all that stuff out for you in a blocking manner so that your tests are easy to reason about. And then it'll either produce a value or throw an exception. And the other thing is that you just describe how the promise works to exec harness.yield, and there's no need to subscribe to the promise. The exec harness will take care of executing it and producing the value for you. So this comes in two varieties. The first variety is just simple yield. And you'll notice if you follow the Java doc syntax, this is an instance method. So there's that, and then there's a static method, yield single. So instead of getting an instance of exec harness, executing your yield, and then closing the exec harness, exec yield single will allow you to execute your closure or your function, and it'll take care of starting it up and cleaning it up for you. There's another variation. There's another method that we can use on exec harness called run. So run is a bit different. If you have a bunch of promises that are being chained and you want to see how they work more in context, I prefer to use run. It's closer to how you would end up writing your promises and your promise flow in Ratpack. So the thing about run is it's a void type, so there's no return type from run. Promises are not automatically subscribed to, and they come in two varieties, right? So you have run and run single, same thing as yield and yield single. And there's a couple of advanced things that we may not get to today, but you have concepts such as promised So promised is some future promise value that is not made available yet, but you can make a promise value from a promised concept and then subscribe to it in the future. This all sounds mind-bending. I know how crazy it sounds. Another thing that is made available is serial batch and parallel batch. What batching allows you to do is it allows you to take a list of promises and produce a promise with all the resolved values of the list. It's a really handy mechanism that's an idiom that's pretty commonly found while you're working with promises. So that's going to be basically my overall overview, and then we're going to get to the examples right now. So I want to start by just using thread primitives and go talk about how difficult multi-threading is, right? A kind of asynchronous behavior. So we have a test here where we spawn n number of threads for n number of elements in a given range. We just want to sum it up in parallel, right? So that's what we're doing here. We have a range. We're producing these closures, and then we're passing the closures to thread.start. We wait for each of these threads to finish, and when they're done, we'd like to make sure that the sum is equal to the range sum, right? And most times, they're not going to be the same at all. And if we were to execute this and see the result, yeah, anybody who's been doing any kind of multi-threading work in the JVM will understand, kind of the pain here. So we fall pretty short of our total sum, which should be 50-50. And I mean, this is just the beginning of your problems if you're going down this road, right? You want to figure out how do we get access to a commonly shared resource such as the sum, and how do we get exclusive access to it, or how do we work within such a way that we can exploit parallelism to faster compute the sum here. So one solution, right? You can make use of atomic variables here, and so we're making use of an atomic integer, and this should produce the correct value. That's what our assertion is here, and it does indeed compute it. But now your logs look strange, right? Like we're updating sum 0, and now it's at 28. And we're updating 0, and now we're at 21, right? And this has to do with not having exclusive access to this variable while you're working with it. So you say, okay, that's kind of lame, but at least we get the right answer. And if you really want to make sure that you lock everything down, right, you just make sure that you have some kind of lock object, such as the sum that we're going to be working with, and you just make sure that you have synchronized access to it so that you get something that produces a nice readable log entry. Right, so this is much nicer, right? So you go from 0 to 1, now we're 1 to 12, now we're 12 to 22, so on and so forth. So it takes a bit of thought, and this is just for summing numbers in parallel. You can imagine and appreciate how much more difficult this becomes when you have real business logic to execute in parallel. Okay, so let's talk about harnesses. So this is the exec harness. If you want to get an instance to it, you would just invoke the static method harness. This produces an instance of the exec harness. In our box specification, we're just going to make use of delegates so that we don't always call exec harness dot yield dot run whatever. And we can also make use of this nice Spock feature for auto cleanup. So this will make sure that no matter what happens in the test, that we always properly clean up the exec harness resource here. So let's create a promise. What does creating a promise look like in Ratpack? There are a couple of mechanisms that you can use to create promises. So one of them is using promise.sync, static method. You produce some kind of factory or a block here that is responsible for creating the promise. What I would like to say here is that when you're queuing up this closure, what you're really doing is you're creating the execution segment, right? So this is the execution segment that we're going to run, and this execution segment then gets queued. So what I want to demonstrate here is that simply creating the promise doesn't really do anything at all. So if we were to run this test, right, came up, well, nothing happened. So we can make an assertion here that this promise was not executed. So what do we do about that? You subscribe to it, and you subscribe to a promise by invoking the then method on it. So what we're doing up here, we're queuing up an execution segment. So this should print sync it returns the value sync, right? And yeah, let's talk about typing, right? Marcin was talking about typing in his Jeb talk here. So we have a promise that produces a string at some point. And when this value is resolved, then we'd like to subscribe to it and make an assertion that we do have sync as the value. So what we end up doing here is we end up creating yet another execution segment by invoking then. So we'll first invoke this, and then we'll invoke this, right? Because Ratpack serializes execution segments, and it executes them in a first in, first out order. But what's this? So if you try to subscribe outside of a Ratpack managed context, you will see this unmanaged thread exception. And a lot of new users run into this pretty frequently. So let's run this test. You run the test, and then the test passes successfully. We see that we expect that this unmanaged thread exception to happen, and it does, right? So this is why you need the exec harness. So this is a correct way to do it. Let's try to fit this in better. So essentially, we're going through the same thing, right? We're creating our promise. We're creating our execution segment here. And you'll notice that because we're making use of yield, all we have to do is produce the promise. We don't subscribe to it explicitly. And what exec harness allows us to do is it produces this execution result, which is then so in your test, yield actually blocks until the promises are resolved that were passed to it. And then we can actually extract the value from it and make our assertion that sync is the value that was produced there. Another variation here, doing the same thing with run, would be if we were to then subscribe to the promise, we can see that we invoke then, and then we can see that our assertion is correct. So we can run this unit test and see that everything passes here, right? You can see the output. We have sync, and then. Okay, so let's go on to the next part here. So you can, let's say, so creating promises typically yields execution segments, yes? But you don't necessarily have to. So if you have some kind of pre-computed static value that you already know of, you can make use of promise.value, and this value will always be used when you subscribe to this promise. So yeah, and that's the other thing about promises as well. They're lazy. You queue them up first, and then you subscribe to them later. So they don't execute until you subscribe to that promise chain. So let's now imagine that we have some kind of third-party async library that has some kind of callback, and here's just a simple example. We create a thread here, and when we're done sleeping, we essentially just invoke the callback with a string saying async computation is complete, and we say that the thread is finished just to make it easy to follow the execution here. So what we'd like to do is oh no, we make use of that later. Okay, so keep that in your mind. Okay, so working with blocking libraries, right? So we're working with, so when you use like promise.sync as an example, that runs on the compute thread. That's pretty much a no-go. So if you want to work with blocking libraries like JDBC, you can make use of this blocking class here and just use this factory here. So blocking.get, and then you can just put your JDBC code in here, and it'll run on the blocking thread pool and keep the compute thread pool from clogging up. So we can see here that blocking.get actually yields a promise. And this is what I was saying. By the time you create a promise, you understand if it's going to run on the CPU thread or a blocking thread. And yeah, where it runs is determined before it's actually scheduled. So here we go. And just using the yield method, we can see that the result is from blocking. So this behaves just like a regular promise in terms of yielding the value. So this is just to demonstrate that each thread has its own. Each thread pool produces a thread name that's easy to see, so you can see where the thread is running. So in this case, we're first running on a blocking thread pool, and then we're mapping on a compute thread pool. And really, what we're expecting to see here is blocking then compute, right? So we block, we extract the thread name. We just do a bit of string manipulation to grab the actual thread pool, and then we pass the result of this into the mapping function And with the mapping function, we now have the result from the blocking thread. And then we grab the current thread from the mapping function, and then we create a Groovy string out of it using string interpolation. And we'd like to see that we're first on blocking, and then we're on compute. Yeah, so that passes. No surprises there. Now, when we're thinking about, I want to bring that async third-party library with callbacks back into play. So another way of creating promises is by using the static method async. So when you have async, what you're denoting is that this is going to be some async code that executes somewhere else. So the async produces an execution segment that runs on the compute thread. And whenever you're ready to signal to the downstream promise chain that you have your value, that you're ready to continue computing the rest of your promise chain, you then invoke downstream.success. So when you invoke async, you're actually given this downstream, and you can use downstream to signal errors. You can use it to signal completeness. You can use it to signal success, stuff like that. So it gives you all the facilities to adapt your asynchronous library to Ratpack. So typically you can use this to create like a wrapper around access to RxMongo as an example, and simply create a service that will just invoke it. So you can use RxMongo as if you were working with Mongo. There's an example of this somewhere in some kind of Ratpack example repository, but I don't know where it is. So here what we're expecting to see is that async start, it gets invoked, async end is printed, and then we have some intermediate stuff going on with some other asynchronous library that has its own threads and concurrency model. So let's give that a try. Yeah. So what I'd like to impress here is that we have our async that started, and then we have the async that ended, and then we now have our thread that executes back up from our third-party asynchronous library, and it just goes to sleep for 5 seconds and then produces the value, and then the thread is finished. Okay, so that's just around how you're creating promises, how you adapt it to blocking libraries, to other asynchronous libraries, and creating them from static values and things like that. So now let's talk about error handling, right? Because I said error handling is nice in Ratpack with promises, and it is. So here we go. So we have, let's say you have some kind of error-prone promise that can throw an exception. Well, using the exec_harness.yield method, you can actually get the value or throw an exception if an exception is thrown. And when this happens, we expect that the exception is thrown because that's what we did. Another thing that we can do here is we can actually provide an error handler. So when an error happens, we can take some kind of remedial action and then be on our way. The important thing to note here is that onError is a terminal operator, which means that if we do invoke an error and this happens, the rest of the promise chain never gets executed. So promises are lazy, right? So if you have an error handler and it gets invoked, none of the downstream promises will get executed. So when we change this promise to do that and do error handling, we can see that when we try to get this value here, we don't have the exception thrown at all. And we see that the value is not equal to map, which we expect to be from here. And we can see that indeed the value is null. There's no value that's produced from here. It's just handled, and execution can happen as normal. Yes, there's a question.
So onError is a terminal operation, but is there any way to somehow provide a fallback value or logic and continue with the flow of execution? So some on failure and then go on with the mapping part of this flow?
That is a great question. So that's our next section here is like how do you continue processing your promise chain in the face of an error, right? So if you have some kind of error and you'd like to have some kind of default value, you can use map error. So this also is an alternative error handler that allows you to continue processing. In some situations, it may not make sense to continue processing your promises, but in other situations where you have unreliable resources that you're getting access to, this would be a way to do it. So you would do map error here and produce this value here. The other thing about map error is that you actually get access to a throwable, to the throwable that was thrown, and you can do that here. So in this situation, we're throwing an exception. We should expect that default value gets produced. And then just to prove that it does continue processing here, we can put it to uppercase as an example of a contrived downstream operation. And when we invoke this, we can see that not only was no exception thrown, but that the rest of our promise chain was executed. So that's how this works. Let's just run this just to show that it works. Yep, green, so it works. So yeah, there's that. Now here's another thing that may surprise people, is promises are immutable. So when you create a promise, you can't actually change this promise. So, well, Dan, what about all these other methods that we invoke? What ends up happening with that? Well, every time you invoke these methods, it ends up creating a new promise, right? And then what you end up doing is chaining these promises together. So if we take an example here, and we have a promise that throws an exception, we think that we're adding an error handler. We think that we're adding a mapping function onto it. But what ends up happening here is that the exception does not get set. In other words, the error handler does not get processed. And we see that indeed the exception does get thrown. So, so how are you supposed to remedy this, right? What you do is instead you chain these promises together, or you can keep reassigning these promises. So if you did something like p equals this and p equals that, then it would work. Then you would get the expected behavior here. Yeah, so in this situation, this promise chain, the fluent way of producing this promise chain, does work. So we can see that here. We can see here that the exception handler was invoked, and that the exception was not thrown at all. Just in the interest of time, I'm just gonna. What I'll do is I'll make sure that you can see that all the tests pass. Just so you believe me. Yeah, well, let's just let that go for now. We're almost done. Yeah, so let's talk about transforming promises. We used transformation methods up to this point, but just to be explicit here, the promise API allows you to work with the promised values when they get computed. So what this means is you can essentially do error handling, you can do mapping from type A to type B. If you have a computation that yields another promise, there's a flat map mechanism that allows you to take that promise and reschedule it on so that it gets continued processing as a part of your chain. So that's flat map as an example. So here when we statically produce the value 3, what we like to do is produce a string of A times whatever it was. And then once we finish that, we see that we're from mapping and we have AAA as an example. So here's an example where a computation results in a promise, and we have to flat map it. If you don't flat map it, what you end up getting here is instead of a string, you get a promise of a string. And this promise never executes unless you explicitly subscribe to it. So if you were then to do this as an example, this would still hold true. And we can prove that here. Now what you end up, new users to Ratpack. Nope, what happened? I'm not gonna, in the interest of time, I'm not going to look into this. Oh, that's right, we have to change this to map, right? So that's the issue here. Oop. Yeah. Okay, well, right, see, so, right. This should be S, this should be P. And we're subscribing to here. So what you can, new users to Ratpack, what they end up doing is they'll end up having a bunch of nested subscriptions. And this is typically not an easy way to work with Ratpack. Ratpack gives you facilities that allow you to kind of linearize your data flow. And we'll cover those mechanisms here. But let's just undo all of this. There you go. Okay. Another facility that Ratpack provides as an example, right? So instead of doing blocking.get, Promise actually has a method called blocking map. So blocking map is a shorthand for doing blocking.get and then putting it there. There are more examples of that. You can do promise composition. So if you're coming from other languages where you have access to tuples and multiple return types, it's really nice. Once you start doing kind of like functional programming, and in Java in specific, you find it like oftentimes you're producing multiple values as a result of computation, and you often have to create a wrapper class for this so that you can package up your multiple values and then pass them on to the next function that then produces them. And that tends to be annoying. Ratpack provides you a way to naturally work with up to 2 values in this way by using pairs. By invoking .write on a promise as an example, produces a pair that gets consumed here. So what we end up doing here is we produce something, and then once that value is computed, we then produce a pair value here, and the left object is what came from blocking, and the right side is what came from here. So this is just another contrived example of how we can kind of work with tuples to a limited degree. Yes, so here's an example of making use of batches, right? And this is an example that we'd like to use here. So if you have some kind of code that looks up corresponding prices for a list of IDs, as an example, like if you're building an e-commerce site, you'll probably get all your IDs in one pass, and then what you can do is you can create a list of promises from that, and then you can use a batching mechanism. So a batching mechanism here are just method references that we're using in Spock. So it'll execute in serial and then in parallel. And then you can, the important thing here is that you have to invoke yield. Yield creates the promise that represents the resolved list of items. You can do conditionals. So if you're working with code and you'd like to map differently based on one condition or another, you can make use of that using mapif. Of course, any kind of variation that you see that's available with mapping, you also have flat map available if you're producing promises there. But here's a simple fizzbuzz example, right? So we're fizzbuzzing here. For a given candidate, what we're doing is just applying fizzbuzz logic. So if the number is divisible by 3 and 5, we produce fizzbuzz, fizz and buzz correspondingly for 3 and 5, and then if nothing else, then we just produce the value, which is the candidate here. So this is an example of kind of doing a conditional promise logic. And if you run the tests, you can see that we do indeed produce fizzbuzz as expected. There's another way of doing conditional routing, and that's simply a method called route. Another caveat to the route method is that it is a terminal operator, meaning that processing stops at there. So that's something to be aware of if you're using route instead of something like mapif or something like that. Another cool thing you can do is you can actually throttle how many promises are running in parallel. So as an example, parallel batch, right, allows you to run your promises in parallel. But here, if you say throttled and pass in a throttled reference, so here we're only allowing 3 promises to run simultaneously, and we can see that we're just going to block for 2 seconds and go through that. This one I do want to demonstrate. So this is the same fizzbuzz example as before. And we'll see that we have 3 promises that are executing in parallel, right? So I'm trying to impress upon you the real value of Ratpack, which is that if you can't find sort of a way that you'd like to represent kind of a flow of your execution, you can always use lower underlying execution API in order to produce the kind of behavior that you'd like to see. Another thing you can do is you can spy on promises by using wiretap. There's an example there. And then operations are basically promise of void type. So these are operation is you can think of it as like a unit or something that just doesn't produce anything. It's just some asynchronous code that you'd like to tie in. And you can turn operations into promises and promises into operations. So this has kind of been a high-level view of promises, operations, how asynchronous works in Ratpack, how you can test it, and how you can kind of create promises and kind of get an intuition for how promises work in Ratpack. And if you're interested, I'll make these unit tests available so that you can play around with them. This is also going to be the basis for a larger kind of like asynchronous cookbook that you can look at and kind of be inspired and kind of find value in Ratpack. But yeah, that's what I have for you today. Are there any questions? I can't really see, but I don't think I see anybody. Okay. Well, I'm available to talk about asynchronous Ratpack or Ratpack in general for the remainder of the day, so feel free to come up and ask away. Thank you.